Right now, on planet Earth, there is less than 1 gram of this element in existence. Total, not 1 gram per country. 1 gram, period. Scientists have never seen a visible piece of it. Nobody knows its true color. And in the next few minutes, I'm going to show you exactly what it looks like, feels like, and behaves like, using nothing but math, logic, and the periodic table itself. This is astatine, the ghost element, and by the end of this video, you'll know more about it than most ordinary chemists do. Here's the problem. Astatine is radioactive. Wildly radioactive. Its most stable form has a half-life of about 8 hours. That means, if you had a visible chunk of it, it would vaporize itself before you could even weigh it. So how do we know anything about it? We don't observe astatine directly. We predict it. And the tool we use to predict it is one of the most powerful ideas in all of chemistry. The periodic trend. Astatine sits at the bottom of group 17, above it, fluorine, chlorine, bromine, iodine, each one a little heavier, a little slower, a little less typically non-metal than the one before it. Fluorine is a pale yellow gas, so reactive it can set water on fire. Chlorine, a greenish gas, still dangerous, still a gas. Bromine, and this is where it gets interesting, is a liquid at room temperature. Dark red-brown, one of only 2 liquid elements on the entire table. Iodine is a solid, a deep purple-black crystal that sublimes into violet vapor. Notice the pattern. Gas, gas, liquid, solid. The elements get heavier down the group. Let's start with atomic radius, because this trend drives everything else about its behavior. Every time you move down a group, you add a new electron shell. Fluorine's radius is 64 picometers, chlorine is 99, bromine 114, and iodine 133. Plot those points, extrapolate the slope, and astatine lands around 145 to 150 picometers. That is not a guess. It's basic curvating on real, measured data. A bigger atom means outermost electrons are farther away, changing how it behaves entirely. Now, for the shocking part, electronegativity usually crashes as you go down a group. Fluorine has the highest electronegativity of any element in existence, 3.98 on the Pauling scale. Bromine sits at 2.96, and iodine drops down further to 2.66. Extend that consistent decline. And astatine's electronegativity lands somewhere around 2.2. That number is wild because 2.2 is almost exactly the electronegativity of hydrogen, a supposed halogen. Pulling on electrons as weakly as hydrogen changes its category completely. Ionization energy tells the same story from the opposite angle. Removing an electron entirely. Fluorine requires 1681 kilojoules per mole, chlorine 1251, bromine 1140, and iodine 1008. Continue it, and astatine should sit close to 892-920 kilojoules per mole. For comparison, that's now creeping toward the ionization energies of actual metals, like lead and bismuth. We're not just predicting a weaker halogen anymore. We're predicting an element standing right at the border between non-metal and metal. And this is the twist that most textbooks still get wrong. For decades, astatine was simply labeled a halogen, presumably a dark solid like iodine, maybe even black or metal. But a 2013 study using relativistic quantum calculations argued something much stranger. Astatine may not form the same kind of tightly bonded diatomic molecules that fluorine, chlorine, bromine, and iodine all form. Instead, it might behave more like a metal, with a metallic bonding character in bulk form. Think about that. The last member of the halogen family might not really be a halogen at all. Chemically speaking, it could be crossing the finish line into metal territory. The same extrapolation trick works on boiling point. Fluorine boils at -188 degrees Celsius. Chlorine -34. Bromine 59. Iodine 184. Each step up is bigger than the last. The curve isn't just rising, it's accelerating. Continue that acceleration, and astatine's predicted boiling point lands around 300 to 350 degrees Celsius. That's a substance with real, hefty, metal-like thermal stability. As for color, iodine is purple-black. Trends, unlimited experimental tracer studies suggest astatine may be even darker, possibly pitch black, possibly with a metallic sheen, though no one has seen it. So here is exactly where that leaves us right now on this planet. We have never seen a visible sample, and we likely never truly will. It simply does not last long enough to collect in any meaningful amount. Yet, using nothing but the periodic table and for data points per property, chemists can confidently predict its size, electronegativity, ionization, energy, and boiling point. We can even question whether it deserves to be called a halogen at all. That's the real power of periodic law, describing an unholdable element with scientific confidence. It might be the halogen that quietly, completely stopped being a halogen, hiding in plain sight.